Okay, welcome everybody to today's webinar. I'm really happy to give you our best knowledge about ball milling and to introduce our portfolio and our best tips and tricks to really give you useful hints how to improve your daily work with our equipment. My name is Dr. Tanja Butt, and I'm working as a product manager at Retsch for many years. And you can, during this webinar, send me your questions. So you can send them via the chat windows, and we will answer it in a private chat room. And yes, so feel free to ask anything you like, and we try to answer everything right now. If it's not possible because too many questions are coming in, of course we go through it afterwards, so that no question remains unanswered. And then let us start with the topics for today. There's the introduction of the ball mills, tips and tricks. Of course, there's also a little bit online demonstration to show our equipment. Then there's a call for Retsch Scientific Award or scientific challenge. And of course, there will be a conclusion and a donor package in the end. And you will also receive this presentation as a PDF in the download package. So if I skip some details, you will have the chance to look this up later on. Okay, the ball mills are used for grinding and pulverization of hard, medium hard, brittle, elastic, and fibrous samples. So here's just a excerpt of some samples we have ground in ball mills so far, and you see that's ranging from minerals over ceramics and coal to pharmaceutical samples, soils, bones, forensic samples, but also fibrous plants like straw, wood, hair, food, plastics, and biological cells like bacteria or yeast cells can also be processed in ball mills to come to the proteins, for example. And the important questions we have to ask ourselves when we like to know what is the best equipment, the best mill, the best accessories for my specific task is that we think about the sample volume we need to pulverize. This can range in ball mills from 20 milliliter to 4 times 220 milliliter, or with our large drum mills to 35 liter. And when we then think about the required fineness we need, then this can range from down to 5 micrometer when we are talking about dry grinding, or less than 100 nanometer particle size, so really small particles. This can only be done in wet grinding. Also, the sample throughput is really of importance, because when you only have one sample each day, this is not important. But when you're running in a campaign and you have hundreds of samples a day, then the sample throughput and the choice of the correct mill is really important for your daily work. And the initial sample size is also very crucial. And in ball mills, we are talking of initial sample sizes up to 20 millimeter. And of course, we have to talk about the subsequent analysis. Is this heavy metals? Is this APIs? Is this proteins? So this can also influence the choice of the mill and the equipment. And do you have sticky or tough samples, volatile ingredients? So we need to talk about tempering. And when we have talk about all this, then in the end, we can find the correct and most suitable equipment for you. So Retsch can say we have the largest range of ball mills. You see here the ball mills we have, and we are talking about a PM100, a Planetary ball mill for standard applications, PM200, which has 2 grinding stations in small jar volumes up to 125 milliliter. Then we have launched the new PM300, a very powerful benchtop unit, which keeps up to 2 500 milliliter jars and has a higher speed than the others with 800 RPM and very ergonomic handling. So we tried everything to improve the handling here. Then we have the PM400 with 4 grinding stations, so maximum 4 times 500 milliliter, or with stacked smaller jars up to 8 samples per batch. And we have the Emax, which is a unique ball mill. It's not a planetary ball mill in the classic way, you know it maybe. Yeah, it works a little bit differently, and it also works with 4-degree cooled water. So you have the option to cool the samples while running. And this is required because we are really talking about an enormous energy input of 2000 RPM or up to 2000 RPM. And this makes the Emax faster and finer than each other ball mill on the market, and you will see this later on. Then also brand new and with the new facelift is the well-known MM400, and this is an all-rounder for small sample volumes. It's a mixer mill, and I think many people use it and work with this. And I think we could, improve the new MM400. So let's talk about this later. And we have the MM500 series, which is the MM500 Vario for high sample throughput because it has 6 grinding stations, and it is also more powerful than the MM400 with 35 Hertz, so that it can grind the samples a little bit faster. We have the MM500 Nano, which is called Nano because it can also go down to 100 nanometer particle size as a planetary ball mills or Emax, with an increased energy input, and it keeps up to 125 milliliter jars, so a little bit more sample volume is possible here. And the MM500 Control, which is more or less the same system, up to 30 Hertz. And here we are talking about active cooling and heating. So we are talking of a temperature range of -100 to +100 degree, where you can process the samples. And we are talking about cooling. Of course, we have to talk about the cryo mill, which grinds the sample at continuous cryogenic grinding at almost -200 degrees, so pretty cold for tough plastic materials, which can be pulverized in this mill as well. Then we have to talk about working principles of ball mills. So there is a working principle of a mixer mill, where you have this horizontal position of the jar, and it is shaken horizontally, and the mainly one large ball, or maybe 2 or 3 balls are in it. They crush the sample maybe by or mostly by impact. Because when they hit here on the ends of the jar, you can imagine that everything what is in between is smashed. You will see this later on also in some videos. Then we have the Emax, which is differently compared to mixer mill and the planetary ball mill, but somehow it's also similar. So what it is here, you have different jars, and they are ovally shaped, and they move on a circular line, and this leads to very good mixing effects, and together with this enormous energy input of up to 2000 RPM, you have really fast grinding effects and very fine particles in the end. And then we have also the planetary ball mill system, of course, where the jars are mounted on a so-called sun wheel. This turns, and while this sun wheel moves around, the jar turns in the opposite direction, usually 2 times each time the sun wheel is turning. So we are talking about a ratio of 1 to -2 because it's turning in the opposite direction, and this leads to strong Coriolis forces inside, also good mixing. And it depends a little bit on the speed you apply and the balls you use, but you mainly get friction and impact, maybe more friction based than, for example, in a mixer mill. But it is really nice also to achieve nanoscale particles. So let's talk about the mixer mills. You can see hopefully here the video running, so how it looks really inside the jars. Yeah, you see the large ball smashes everything in between. So the new MM400, the old one was launched many years ago, and after 15 years we thought it's time for a facelift. So it was introduced this year, and it is of course a more modern look, and it comes along with a touch display. You can grind up to 99 hours, which is important for some specific tasks in mechanochemistry, for example. You can store SOPs and cycle programs. We have it made so-called Raman ready, and we have a reduced noise level. And also it's possible, and it's the first mixer mill on the market, or the first mill on the market, let's say like this, which can be calibrated in speed and time. And this means it comes along with a calibration certificate. And you know exactly when you set 30 Hertz, what is the real value the machine really does. And you can also recalibrate after maybe 1 year and see if something changed or not. So if you are really applying for the best and most reproducible results, then this is a very nice option to you to monitor the reproducibility of your devices. And the reduced noise level, I think it's also a nice factor. Because yeah, when you're working daily with this mill, then even a few decibel less is much more pleasant for you to work with, and you really hear the difference. And many people said already that this is much more pleasant in terms of the noise than the previous model. We have also new accessories. So we have the Falcon tube adapter, which keeps 50 milliliter Falcon tubes. You will see this later on in some applications, and 30 milliliter wide mouth bottle adapters. So here you have the option to, for example, for the life science applications, to isolate proteins, for example, or also to grind some stuff like liver or soft soil samples in it. We have the adapter, which is really pretty new for keeping 5 times 5 milliliter steel tubes, so simultaneously 8 samples can be processed. We have the new transparent PMMA 10 milliliter jars, which are very useful for mechanochemistry, for Raman in situ spectroscopy, and also for light-induced reactions, which can be also done in the field of mechanochemistry. And we have new stainless steel 2 milliliter tubes, which are really grinding jars. They are sealed and capped for cryogenic grinding, which can be used with the PTFE adapter. And this makes working with the system really safe, because the plastic tubes cannot break anymore. And what is the so-called Raman readiness? You can remove the bottom plate over here, then you have access to the jars from underneath. And here you can place a spectroscopy device for the Raman. This points on the bottom of the jars. So this is really nice for this as well, to see what is really going on when you work in mechanochemical reactions, for example. Okay, then let's talk about the Emacs. The Emacs, let's start. Also, the video works differently than explained with the mixer mill. So we have the enormous energy input of 2000 RPM. And you see that, yeah, here the jars are overly shaped, and they are moving on a round circle. And this leads to really a very good mixing inside of the jars, and very fast pulverization of the samples. And what is also very nice for the Emacs, that we work really with water cooling. So it's always water cooled in an internal loop, and you have also the option to counter cool with an external water loop, the internal one. So with the chiller, for example, where the water temperature is set to 4 degrees, then we have a really efficient water cooling system, and the samples inside are staying much cooler than in a Planetary ball mill, for example. And we have also the so-called temperature control mode, but we cannot work with cryogenic grinding, and we have no heating options as for the MM500 control, for example. And what is the so-called temperature control mode? You can set and define an upper limit of a temperature, for example, 80 degree, and a lower limit of a temperature, for example, 50 degree, and then it starts grinding. And as soon as it recognizes that the jar outside is reaching the 80 degree, it stops grinding. And then when the temperature drops again and the lower limit is achieved, then it starts grinding again. So it only grinds between the two limits of the temperatures, and you can be pretty sure that at a certain degree inside the jar or the sample inside is not overheating. And also you can see that these grinding breaks which are required are really adapted to the sample and your requirements. It's not only set maybe 10 minutes and you lose some time because it was set too long. Yeah, it's not required. Maybe only 5 minutes are okay. So it automatically recognizes the suitable time which is required to stay below a certain level and to adapt the break times. So you can skip all imperial trials before to find out the correct break times, for example. And this much more straightforward and doing the perfect grinding process for sample sensitive materials. And of course, we have to talk about planetary ball mills. Also here we have a short animation about the grinding mechanism over here. So you see here the movement of the jar on the planetary, on the sun wheel and the planetary mill. And you also see that the ball package inside is moving. There's some impact, there's a lot of friction in between, and this is also very good mixing and a lot of friction which is required to go down to nanoparticle size. Here we have a new planetary ball mill, the PM300, and this is launched in the summer, and we are really proud of this machine. So we have a very high energy input for a planetary ball mill. It's 800 RPM. We have the 2 large jars which can be used. We have also larger sun wheel which brings in more energy input. So we can also use it for many tasks in nano grinding and fast grinding and mechanochemistry and so on. But we have also improved the ergonomics, so the safety and the handling. Of course, it has a touch display, which is programmable for the program cycle programs and so on. And the total process time when you work with cycle programs and include the grinding breaks to let some sample cool down is automatically calculated and shown. So you do not have to calculate by yourself, okay, I have so many cycles, X grinding time, epsilon break time, and how long is it in total. So it is shown, very nice. You have a locked sun wheel, so the clamping mechanism is facilitated because it's just locked. And we have an automatic notification about the correct clamping, which is also very nice, especially when you're working with a high energy input of 800 RPM. Of course, it is easy to clean because we have an easy access to all the jars, and the hood is with a smooth surface inside. Yes, and we have also new accessories. So a complete new jar range for all our planetary ball mills has been introduced with this mill, the Easy Fit line, which comes along with the advanced anti-stress structure. This is here at the bottom of the jars. So the wear over the time is greatly reduced, even at 800 RPM, and also the handling is a little bit facilitated. We have also the option to work with a broader range of aeration lids and grind control system. We will see this later on. And when you ask yourself, okay, I have different planetary ball mill systems, and okay, now they changed the sun wheel, they changed maybe also the speed, and which speed do I have to apply when I now working with the new PM300, for example, and I'm used to work with the PM100. How can I really assure that I have the same energy input? Then we have also this diagram for you where you can see, okay, here the blue line, for example, this is the speed here up to 800 RPM with the PM300, and you see that is going up to more than 64 G. So a very high energy input. this is not reachable by the other planetary ball mills, but for example, when you compare to the PM100 here, when you apply the maximum speed of 650, you see that you have to set a little bit less than 600 RPM with the PM300 to have the same energy input. And here at this point, for example, where also the maximum G level of the PM400 is 26.8 G, you see that you have to apply different speeds on the other systems. And I think this makes it easy just to get the same result on the different systems. And when you wonder, for example, 800 RPM, why is it really required? We have already 650 with the PM 100. For example, you can see that increasing the speed has an influence. Usually on wet grinding results in small jars, also for dry grinding, it's faster when you use 50 milliliter jars, for example, here. And in mechanochemistry reasons also, it's really nice. This is a net grinding time. Of course, when you increase the speed, you have also to talk about more warming effects. So in the end, maybe you need longer grinding breaks in between. So it depends on your specific requirements, if it is really useful to work with a higher speed, or if it is maybe better to work with a moderate speed in the end. And when we are talking about speed, we also have to talk about the load with the PM300. So the load defines the speed. We have no artificial limits, for example, that you have to type in a bore size or something like that. So the machine gets the speed which is coming out of the power supply, let's say it like that. And with a 125 milliliter jar, it works fine. You can always reach the 800 RPM when you are working in a larger jar. Then you have more load on the machine, and it depends on the ball size you use, which speed can be really reached. And when you're working with the 500 milliliter jars, then you reach at least 600 RPM because of the load. And you also see when you're working with tungsten carbide jars, which are more heavy than the steel ones, you reach lower limits or lower speed with the system. But you can always be sure that the maximum which is possible with the load is really available with the system, and there are no artificial limits. And yes, the machine does 800 RPM in each case. Not in each case, because even if you have a Ferrari, you cannot go full speed uphill when you have 4 persons sitting in. So it really depends on the load, which speed is applicable, and of course to your task, because sometimes 800 RPM or even 650 is not the best because it leads to caking effect, and then a moderate speed is much better. So it depends on your cases. Okay, this was a short introduction about the 3 different ball mills we mainly sell, but now I'd like to go to useful tips and tricks for ball milling. So let's start with the definition or the impact on friction. You have heard that I talked about impact on friction. Mixer mills more impact, the planetary ball mills more friction-like, and Emacs a little bit of both. The good mixing. So what is the difference now? So imagine you have a large particle, an initial particle. Friction does not really help. You need impact to crush it initially. So large particles, impact is required, and for that we need large balls. And after a while, you can switch more to friction effects, because now you need smaller particles, maybe also for fibrous particles on samples, friction is beneficial, and for that you need smaller balls, because for friction you need more surface of the balls and a little bit of touching points in between to really have this friction effects. And when you like to go for ultra fine particles, you also need friction and wet grinding, because in dry grinding you have a hurdle down to 5 microns approximately, depends on the sample. You can achieve the particle size with dry grinding, and then you will have some surface effects like loading, positive charging, negative charging, agglomeration effects. And to overcome this, you need to go for wet grinding. You will see this later on. So for ultra fine particles down to nanometer area, you need friction, you need a liquid to keep the particles separated, you need the smallest balls, and a very, very good mixing effect. So for the ball mills, Retsch has, we are talking about ball sizes ranging from 0.1 to 30 millimeter. So when we are talking from coarse to fine, the initial particle size, for example, is 10 millimeter, like that. You are thinking about the largest particle you can find in your sample. Then we have to think about that the balls need to be at least 3 times larger than the largest particles to have enough crushing efficiency. Yeah, so we end up here with 30 millimeter balls. And now which fineness can be achieved? Approximately 1,000th part of the particle size. So this is in this case, for example, here 30 of the particle of the ball size. So we end up at 30 microns here. Okay, and now 30 microns, but I need finer particles. And when you really need finer particles, you have to switch the ball size in between. So first start with large balls to come to a certain fineness, and then you can use finer or smaller balls to come further down and to really pulverize your sample, maybe to the nanometer scale as well. So you can change now to 100 micron balls. It's still 3 times bigger than the particles, which are already 30 microns. And then you can get again maybe a smaller balls, particles like 10 nanometer. So this is really a crucial point, that you have to change the ball size in between when you really like to come from a larger, coarser particle to very fine particles. The choice of the material for grinding tools is also of great importance. You have the energy input, so the density, and here we can sort our different materials: tungsten carbide, steel, zirconium oxide, most common ones, and you see that tungsten carbide is a heavy material. Of course, when you accelerate this heavy material, then you have more energy input. When you have 30 millimeter ball of this material falling on your foot, you feel the pain. If you use, for example, agate, much lighter material of the same ball size, and this drops to your foot, it doesn't feel it with the shoe around. Yeah, so this is the energy input via the density. And softer samples like soils or pharmaceutical products need moderate energy input. Harder samples like ores or alloys need higher energy input. And we have to talk about the hardness, because the material you grind with should be harder than your sample, because otherwise your sample grinds the balls. And this is, of course, not what you really like. So the grinding tools should be harder than the samples, and there's never abrasion-free grinding possible. Yeah, so we are always talking about abrasion, about mechanical size minimization, and the point here is which abrasion does disturb your sample material. So which material is neutral to analysis? For example, if you're using zirconium oxide, you get abrasion of zirconium oxide, but you're not looking for that because you are analyzing for heavy metals. And then this is not a problem anymore. And it's not that you get grams of the materials and the balls in the sample, but to a certain degree in the ppm or ppb range, you will find it. And it's only important to work with a neutral to analysis material. Then let's talk about dry grinding. And here we have also some tips and tricks for you. So there's a called 1/3 rule. So you know your amount of sample which you need to grind, and the jar should be approximately 3 times larger. So you fill the jar up to 30% with the sample. You fill approximately 30% of the jar volume with balls, and then you have some free space, of course, in the dry grinding, so that the jar movement is really assured, and you can really accelerate the balls inside, and you have really the crushing energy. And there's also one important point, that you do not mix the materials. And if you work with a steel jar, you do not work with zirconium oxide balls, because then you get 2 kinds of abrasion, zirconium and the steel. Yeah, so we never mix the different materials with the jars and the balls. And also the abrasion factor is minimized and you have less wear when you obey to this rule. And you also do not mix the ball sizes. Maybe some of you have asked yourself, okay, I have to switch the ball size to come from a coarse to a fine particle in the end. Why not mixing them? Because the large balls will also crush the smaller balls. This is not what you like. You want to pulverize your sample, but not the balls. So never mix the ball sizes, maybe except in a very slowly running drum mill, but not with the mills we are discussing today. And when you think about yourself now, okay, I know my sample volume, I know my initial size of the particles, then we have all these tables in the manuals on the web pages and so on, where you can, look yourself, look which jar is now required. For example, you have 1 millimeter particles. You can work in the 12 milliliter and 25 milliliter jar. Yes, fine. If you have larger particles, those two are maybe not the best, because you need to apply 3 times bigger balls to really crush it in the beginning, and this cannot be put anymore in the very small jars. So you can judge which jar size over here is the best for you, and also the sample amount. And then you can see, okay, I know I really have the 3 millimeter particle size in the beginning. I need to go for 10 millimeter size balls, and I have to put in 20 per jar. Yeah, so this is how you can read these tables. So the amount of the sample and the initial particle size determines the choice of the volume of the jar and also the size of the balls which you have to use initially. Then let's talk about fiber samples. Fiber samples lose their volume during grinding, and you have risk of damages because if you have not enough material in between, the balls will crush something in the end, so maybe themselves. So you have to assure that at least enough material is always in the jar. And when you only fill 1/3 of the fiber material and it loses the volume, you have not enough anymore after 2 minutes of grinding. So you have to fill the jar from the beginning on completely with the fiber sample, and then when it is losing the volume, it fits perfectly to the 1/3 rule. And maybe it's worth to refill it from time to time, really, when it's very fluffy material. And here we can also talk about different jar systems. We have here's the one for the MM400, for example, where we have some of the nominal volume which is placed on the lid. So you cannot really use this 1/3 volume in the lid because you cannot use it for filling, for example. Yeah, fiber samples maybe spills over, and for wet grinding, you can maybe not bring in enough material in. So here maybe when you're thinking about fiber samples or wet grinding, the other systems like the MM500 Control Nano or the Emax is much better, because here you have the flat lid and the total nominal volume here, for example, of 125 milliliter or 50 milliliter can be really used and filled up. Yeah. So this is just the same amount of fiber sample put into the 50 milliliter jar, and you see what I mean. Yeah, filling fiber sample is much easier with these screw lock jars, which are used for the MM500 Nano, for example. And with these jars here, also with this flat lid, and which allows for an optimized filling level for wet grinding. I come to this in a few minutes. It is really possible also in a mixer mill to go down to nanometer scale, which is not possible in the MM400 and the MM400 jars. Yeah, you see this here with this jar, nanometer scale, 130 nanometer in this case have been reached. So keep in mind that the MM400 is not thought for wet grinding in this case. Okay, before we come to the wet grinding, let's see some example for the dry grinding, like this brittle stone, for example, here, which has been processed in the PM400 and 4 25 milliliter grinding jars with large balls. And yeah, you see that just in 3 minutes, we have pulverized this brittle stone of an initial size of 10 millimeter. Also concrete here has been processed in the MM400 in a 50 milliliter grinding jar in only 10 seconds. Yeah, it's really, really quick pulverization over here, and really nice result of 100 microns. Brittle and tough materials like this electronic scrap need maybe a pre-cutting in our cutting mill SM300 so that this fits into the jars of a PM100, for example, because here the analytics is heavy metals. This means we work with tungsten carbide equipment, yeah, because of this abrasion factor and the neutral to analysis workaround. And you see that we also can pulverize it in 10 minutes easily. And these LEDs can also be pulverized in a PM100, but you see that the metal parts stay intact. And this is also very important. We cannot grind metals. Even if you go cryogenically, you cannot brittle a metal. This will stay, more or less intact. Of course, you have it deformed, but you do not pulverize the metal in the ball mills. It doesn't work, okay? Medium hard and brittle, like this pharmaceutical products in the PM200 in this time, an agate system, because many pharmaceutical companies like to work with agate, very pure natural material, and feed pellets could also be pulverized easily in the MM400. Yes, you see that's really quick pulverization here with the MM400, and with the little bit harder material here in the PM200, we need a little bit more time. And also fibrous or tough materials like plant leaves or this wood sample can be really easily pulverized as well. You see that, of course, larger wood particles have to be pre-cut again in a cutting mill, for example. And here we really get nice powdered wood in the end. And some nice application here for the MM400, especially with this Falcon tube adapter I mentioned before. You see that we can pulverize 8 samples in one batch, for example, the soil sample, but it's important that there are no stones in it, because plastic tube stones in it, and you really move this fast, then the stone could lead to breaks in the Falcon tube adapters. But in principle, it's also suitable for grinding such a soft sample like soil or dried flower buds for cannabis, which is a very nice topic in the moment. Everybody's talking about cannabis, and of course we have to talk about analytics of cannabis as well. Here the sample can be really easily homogenized with the MM400. Then let's talk about cryogenic grinding. Cryogenic grinding of samples needs very, very cold temperatures. For example, we can achieve this with liquid nitrogen, so almost -200 degrees. And this is required for this, plastic materials like this rubber duck or the chewing gum, some foods, or even meat. Where room temperature is not okay, because you cannot pulverize this samples at room temperature. It will only stick, it will not be homogeneous, it will cake, it will be deformed only, but nothing will happen with a rubber duck, for example. So you need to embrittle this with this pretty cold temperatures so that you can pulverize also these samples in a ball mill. So for sticky, fatty, tough, elastic samples, pulverization is only cryogenically available. Temperature-sensitive samples also, you can think about cryogenic grinding so that the volatile ingredients stay in the sample during the grinding process. There are the same filling routes as for dry grinding, and the most important point is that in ball mills, we always talk about indirect cryogenic grinding. So we do not put the sample into the liquid nitrogen and fill something in the jar and close it, because this will bring overpressure to the jar. So we are putting the sample in the jar, closing it, also of course the ball is in, closing it tightly, and then we bring the closed jar to a liquid bath with liquid nitrogen and let it cool down from the outside. You never fill in liquid nitrogen in the jar, And here you can see the procedure: put the sample in the grinding ball inside, close it tightly, put it into the bath with the liquid nitrogen, let it cool down, maybe 3, maybe 5 minutes until the liquid nitrogen stops boiling. Then it is also pretty cold inside. And then you can grind for 1 or 2 minutes. And if you need longer grinding times, you need intermediate cooling in the liquid nitrogen baths. So here it is important to mention that in the MM400 we can only work with steel equipment, because when you insert this zirconium oxide jar into the cooling bath and cool it down for more than 200 degrees from room temperature down to minus 196 degrees, this will lead to cracks here in the zirconium oxide in this system. So please only work with steel jars here. There are videos in the download package later on, so you can see it, everything, how it is really done. And let's talk about the cryomill, because the cryomill is a system which automatically cools the jars. You do not have to work with the open liquid nitrogen bath anymore, so it's also safety reason. And you can be sure that there's constant cryogenic grinding conditions. So for this intermediate cooling steps, they are maybe not required. So you do not have to take the jar out and put it again into the liquid nitrogen. We have an automated pre-cooling which you can set. And yes, this is really nice and a safe system. And you see that the liquid nitrogen here always cools the jar, which is clamped over here. And here for this system, we can also work with zirconium oxide jars, which are specially made available for this system. And we have also to talk about the MM500 control. You remember I introduced it in the beginning slides, but here we can work in a temperature range from minus 100 degrees to plus 100 degrees. But in terms of cryogenic cooling, we are talking from minus 100 to 0 degree. And for that you need, or you can take the so-called cryopad, which helps to control the flow of the liquid nitrogen through the machine. You can see here the jar is placed on the so-called or above the so-called thermal plates. And the liquid nitrogen here flushes the thermal plates. And of course, it takes away the heat from the jar, because it's pretty cold, and you cool the jar from underneath. It's the same way when you apply with a hot liquid, thermal oil, for example. It brings energy to the jar, it brings warmth to the jar, but in this case, it takes away the heat, and it keeps the jar pretty cold. And you can really work with moderate temperatures over here in this system. You can set, for example, hey, thermal plate stay at minus 40 degree or minus 60 degree. So you do not have to go that much down to a minus 196 degree as in the cryomill. And here we can work with zirconium oxide and tungsten carbide jars, because the cooling is more moderate and it's not ad hoc like in the liquid nitrogen bath with the MM400. Some examples over here. These suites have been immersed in liquid nitrogen for 2 minutes, and after 60 seconds it has been pulverized. And even here with the hair sample, it is quite nice for drug analysis, for example, or hazardous substances which can be analyzed in hair even after years. And here cryogenic grinding is really nice. And if you need a higher throughput because you have many samples a day, think about the MM500 Vario with the 6 grinding stations. Yes. And when we're talking about the MM500 Vario, we are also talking about a higher energy input of 35 Hertz compared to MM400, for example, with maximum of 30 Hertz. And you can think, okay, it's only 5 Hertz difference. Where is really the factor? What is the benefit for me? Especially when we're talking about cryogenic grinding, so more tough materials. You see that after 2 minutes cryogenic grinding of the same sample, we have some leftovers here, the lumps, they had not been ground. You can get rid of it when you elongate the grinding time. So after 8 minutes or something like that, they also will be pulverized. But 2 minutes, they stay over. The same sample with 30 Hertz, 2 minutes, nothing is left over. Yeah, this is already homogenized. And when you grind maybe 1 or 2 minutes longer, then it's also fully pulverized, what is possible in this system. So when we compare the finest, so the best finest is achieved in one case after 5 minutes and the other one after 8 minutes. So it's approximately 2 times faster thanks to the increased energy input. And we see this for many, many samples, not only for this plastic. So the factor of 2 times here, thanks to the high energy input, is really crucial. So then let's see what happens to this the rubber duck. You see that you can also put the rubber duck in the cutting mill to come to pre-crushed or pre-ground particles which fit into the cryomill jars, for example. Let them pre-cool automatically for 5 minutes, and then we can grind also here in cycles. For example, 1 minute grinding and then 30 seconds intermediate cooling, but the jar stays in the machine. You do not have to take it out. Everything is automatically done. And then you pulverize this rubber duck really to 300 microns. And I think that's quite impressive. And also with this licorice, so food sample, which is very sticky, can be done, for example, in an MM500 control at -60 degree. And same principle, yeah, you need the cryopad, you need maybe also some cycles of grinding and cooling, and everything stays in the machine and you do not have to take it out as for the MM400. And then we like to compare the two different systems with the automatic cooling, like the MM500 control and the cryomill. You see that the maximum or the lowest temperature we ever achieve in the control is -100, and then the cryomill is almost double that temperature. And this means for very, very tough materials like many plastics, you come to better results in the end. And you also see that there's a difference in the MM500 control if I am talking about a 50 milliliter jar or a 125 milliliter jar, where I have to work with several large balls and not only with one large balls anymore. Yeah, that the best fineness I can achieve in the smaller jar is better than in the larger one. Or for another example, I cannot really grind the sample material in the larger one because I get only flakes. Yeah, the -100 degrees is not sufficient to embrittle the sample in this case. And in each case, you will get much better results in the cryomill, but for some materials, especially for food samples, but also for some plastics, the MM500 control is also suitable. Keep this in mind, maybe. Then let's go over to the online demonstration. For that, I will switch to the lab where all the ball mills are placed, and just give me some seconds to go there. I will be back soon. Okay, so now I'm in the lab, and as promised, I'd like to show you some of the machines I have talked to today. I will not do any grindings because this takes too much time, and you will see this later on in the download package in the videos I've put in. But what I can show you is different accessories and how to put in the jars into the different machines. So let's start with the MM400. I asked my colleague Lena just to come a little bit more forward so that you can see the new device. So you remember I've shown this in the presentation as well. And yeah, this is a really versatile machine. So you can work with the grinding jars. The most common one are the 50 milliliter jars. Yeah, so here you can see the cavities, and we are working with one large ball usually. So you put in the ball, the sample, close the jar, and then you just put it into the machine, which is quite easy. It's a self-centering system. Like this. Now the machine cannot open anymore, and it's really fixed and secured. We have also different jars, for example, zirconium oxide jar. You see also the ball in it. Or we have smaller jars. This one is a 25 milliliter jar. And together with the new MM400, we have designed this adapter. Yeah, you see with this adapter, it keeps 4 grinding jars. These are the 5 milliliter grinding jars. And what you put in here, for example, is, where are they? 2 balls size 10 millimeter stainless steel, or 3 or 1, it depends on your requirements. Then you put in, of course, the sample in it, close it, put it in the adapter, close the adapter with this device, and then you can put it into the machine as shown before. What we also have, the new transparent jars. You have seen them in the presentation, can also be used with 10 millimeter balls, zirconium oxide, stainless steel, or agate, for example. And of course, we have the different systems for our biological means. This is the adapter for the Falcon tubes, which is then placed into the machine, and you can easily attach and detach the tubes. There are also some videos included later on. You will see this, and this is nice and fine. And last but not least, we have the adapter for the single-use vials. So here is the 2 milliliter tube for cell disruption, up to 10 times in this adapter. And then the adapter is also placed in the machine like that. And brand new are the 2 milliliter steel tubes. Yeah, also sealed and screwed. Whoops. Take it again. And here you can put in 7 millimeter steel balls, maximum or smaller, and use this tubes as well for biological meanings or mechanochemistry or whatever you like. Then let's just move to the larger sister of the machine. This is the MM500 Vario. As seen in the presentation, we have the 6 grinding stations, 3 on each side, and all the different jars I showed can also be put into this machine nice and smoothly as shown previously. Also, this one can be put into the MM500 Vario, but only if you have the new type of MM500 Vario with the new holding system. So when you buy it right now, this fits. If you have an older system and you like to use the 5 milliliter jars, you have to talk with us, then we maybe can exchange it on your device, and then it's also possible to use it. Also, you can use the adapter for the single-use vials or the 2 milliliter steel tubes. What you cannot use is the adapter for the Falcon tubes. This only fits in the MM400. And this does not fit in the MM500. But the advantage here is you have 6 grinding stations. You have a little bit more power with the 35 Hertz as shown in the presentation. So you can say that the machine is 2 times faster than the MM400. And also you have more grinding stations. So for high throughput, this is a very nice system. Then I asked my colleague to show the MM500 Nano. This is this system over here. So you can see that it's looking a little bit different from the jar holding system. 2 again. And now we are working with different jars as shown in the presentation. It's not the screw top jars anymore, but it's just the screw lock jars. Lena is just moving towards me. This one here, for example, is 80 milliliter sample or volume, like this. And you see that the lid is flat, so no volume of the nominal value gets lost in the lid, and you simply screw the jars like that evenly. And then you can also use, where is it? Here, a system like that to really get it tightened. And this is more or less the movement which is still required after hand tight, and now it is really tight. yeah, up to 5 bar. The placement in the machine is also quite easy. You just put it in and screw here, and then it's securely fixed. Okay, what we also have for this type of mill is an adapter for the steel tubes or for the single-use vials. Yeah, 18 of the single-use vials or 9 of the 2 milliliter steel tubes can be placed in, then it's closed. And then you see it has a similar shape as the adapter, as the jar, and then you can also just simply put it in. Okay, and what we also have quite brand new on the market are the multi-cavity jars. So you can see here that it has 2 cavities. There's also this cap inside. So here you can use 2 samples in one run. And afterwards you just put a cap on it and then you can pour out the sample quite easily. And also we have one new jar working with 4 times 10 milliliter cavities and also the caps for the pouring. Of course, we have here also different jar sizes and different jar materials like zirconium oxide and tungsten carbide as usual. Then, I think, very interesting device, I asked my colleague just to come over here, is the MM500 control, which works with the same equipment as the MM500 Nano, so the same jars can be placed in here. But the most interesting point is here this part, yeah, the thermal plates where the energy or the warming can be just dissipated from the jars. So here is the part where you can flush the mill with liquid nitrogen or with, for example, any cooling agent or any thermal oil for heating purposes. And this means you can bring heat to the jar or you can take heat from the jar away. And you have also some indications in the display how the temperature is developing, if it is increasing or stays at the same level and so on. So many nice options to control the temperature of the device. You will see this in the videos of the download package. Due to time reasons, I cannot really show it right now because it takes some time to cool it down and to see how it develops. Keep in mind, this machine goes down to -100 degrees. When you need to embottle the sample more for plastics, for example, so if you really have really tough sample materials, you would better use the cryomill, which goes down to almost -200 degrees. You have one grinding station and the jars are looking a little bit different. So from the inside, you know this, they are looking more or less like the jars of the MM400. Yeah, you place a ball and the sample in it, then you close the jar. And now you screw it from this side here into this machine. Nice. And then you have only, can you see this? Use these 2 screws to make sure that the jar is really fixed inside. Well, that's all. Also a nice and quick procedure over here. And also we have here different jar sizes. We have also zirconium oxide jar usable, and you can work in the same 5 milliliter steel tubes as shown for the MM400 already. And also the single-use vials can be used and more or less coming soon in some weeks. Also the 2 milliliter steel tubes can be used. Okay, this was a quick run through our mixer mills, and I also promised you to show our other devices, the Planetary ball mills and the Emax. This is the new device I've spoken in the about in the presentation, the PM300, where we are really proud of. So you see it's a benchtop model, and 2 grinding jars can be just placed in, up to 500 milliliters. So this is a jar like that. Yeah, this is 500 milliliter jar. And you also see here the bottom structure, the AAT, anti-twist, advanced anti-twist structure over here. So that placement in the machine is quite easy. I show it. And then you only need a short twist, and it is just finding its position quickly. Also, this is shown in a detailed way in the videos which are attached. You can now use this clamping system and use it for quite quick clamping. Just a second. Yeah, more or less that's it to fix a jar. We can also work with, of course, other jar sizes down to 12 milliliter. So this machine ranges from 12 to 500 milliliter. When we like to work with the very tiny small jars, this is a 12 milliliter, or let's see. Yeah, it's really a 12 milliliter jar, very tiny in comparison to the jar I showed you before. You just need an adapter to get the bottom structure, and then you can just insert the jar like that. Everything is fine, and you can also put 2 jars in the machine. You can also use an adapter for stacking the 50 and 80 milliliter jars. Then you need an adapter like that. Where is it? So and now this stack can also be used in the PM300. So in principle, this is a very versatile machine because it is easy to use, up to 800 RPM. You can go up to 2 jars, 500 milliliter. You can work with the smaller ones, 4 in the maximum when you stack them, and it's really easy and nice to be used. Then I just like to show one of the older Planetary ball mill system Retsch has. So here, this is a PM100 with 1 grinding station. And you see that we have to counterbalance the 1 jar inside because it needs to be balanced, and we're only working with 1 grinding jar position. It's the same jars also with the new structures. The clamping mechanism is quite similar. Yeah, you also use this clamping unit over here. And I think here the handling is also nice and easy, but the PM300 has some special handling devices like the fixed sun wheel, which helps you to clamp the jar and so on. You have seen this in the presentation. You will see this in the videos later on. And then last but not least, we have to cope with our system here with all the cables. I'd like to show the Emacs. Yeah, this is the Emacs, which works with similar jars as the MM500, Nano, and Control. So you see the shape. I just open it. Of the 125 milliliter jar, you see also the flat lid, and screwing is also done very quickly. Like that. Then it is just placed in the machine and secured by bringing down this clamping system. And that's it. So also here the clamping is quite quickly done, as for all the other machines. And I think you get an impression about handling the machines. I will not focus on the grinding results right now. I will not focus on all the touch displays. This takes really too much time. Who is interested in that, please have a closer look to the download package, or just phone us. We can do an online demonstration for a specific device, or you can visit us or our colleagues worldwide. So I think there will be some solutions to really show you the instrument of interest. And then I'd like to switch back to the presentation. So see you. Great. So back in the presentation room. Now I'd like to talk about wet grinding. Wet grinding is used for nanoscale grinding or for particles below 5 microns. And you also see that, here, two examples with the MM500 Nano and the Emax, and you see that the Emax here is very, very quick. And it achieves the best fineness after only 5 minutes in this case. But the MM500 Nano, so mixer mill, can also be used for the nanoscale grinding here. It takes a little bit longer, but it works fine. So how to conduct wet grinding and why? So if the particle size decreases, the relation surface to the volume increases as well. And this means that small particles below approximately 5 microns tend to agglomerate due to the electrostatic charges. And this means you need to separate the molecules because otherwise you cannot really grind them further down. And you can use water, buffer, alcohols, long chain molecules, suspensions, whatever, to keep the particles separated. A buffer, for example, to neutralize the charges. Then this particle is now not neutralized and it will not agglomerate anymore, or you keep it separate with a long chain molecules via steric stabilization. And this is really crucial that if you like to go further down than this 5 micron, then you need to go for wet grinding. And this is applicable for the Planetary ball mills, for the Emax, the MM500 Nano, and the Control. Yes. And here we have also some rules. You remember that we are again with the 1/3 filling rule. So 30% of the jar volume is again the sample, but now we increase the number of the balls to 60% of the jar volume, because you remember we need the friction and the large surfaces and the friction points. So we need more grinding balls in between to achieve more friction. And we do not work with the large balls because we need more balls, large surface, many balls. Yes. And we also take an abrasion resistant material like zirconium oxide because more friction means more abrasion in the end. So steel can be done, tungsten carbide can be done, but the most common one is zirconium oxide. And we use balls which are smaller than 3 millimeter, maybe 1 millimeter is nice, but we can really go down to very, very fine balls of 0.1 millimeter size. And now we also have to add the liquid, of course. And how much liquid, or how do we really do it? So first, fill in the balls. That's easier than first filling in the sample. Then you add the 30% sample. Then you see that it somehow settles between the balls. Then you add the liquid. For example, in a 250 milliliter jar, you can add 70 milliliter water. Depends a bit on the sample, depends a bit on the liquid, but around 70 milliliter in this jar size. And then you have to mix it, and then it's ready for grinding. And tips for the wet grinding: if you have a sample which tends to sediment, then there should be a liquid layer on the ball sample mixture. This is too dry. This will not work. It does not move. There's no friction. You have to make it more liquid. And when you have a sample which does not sediment, then maybe it looks like that. Then it's also an easy tip. Just take a spoon, and while you mix it, when you get this slight streaks which disappear after a few seconds, then that's fine. It's like motor oil or ketchup. Not too liquid, not too dry. That's fine. And this is again the example with the 70 milliliter water. And what is very important, the dispersant must be, of course, chosen that it does not dissolve the sample. So if you're grinding salts and you put it in water, then you have it dissolved and not ground. And how do you really put the many small grinding jars into it for the 60% filling level? You do not count it, you do it just by weight. Yeah, you know the volume of the grinding jar, you know the weight of the balls, and you just weight the balls in, for example, 50 millimeter zirconium oxide, 3 millimeter balls. Then you need 110 gram of the balls, much better than counting, of course. Then let's talk about closing the jars for wet grinding. Here we are talking about Planetary ball mills. They have a very nice safety closure device. It's looking like that, very easy to put on the jar. And here you can really safely close it tightly up to 5 bar, and when you now talk about wet grinding, maybe some pressure inside occurs and you like not any spillages or sample coming out of the jar, you can just press it here together, the liquid, the lid and the jar, and you can take it out after grinding and put it in a water bath, for example, for cooling down. And with the Emax or MM500 Nano control, you do not need any special device because this safety closure is just part of the lid. Yeah, you can see that you really screw the lid to the jar and everything is nice over here. Sample recovery for wet grinding is also a topic we are asked frequently. So for example, you can use a sieve and a bottom, just pour the dispersal and the sample ball liquid mixture of the grinding process on the sieve. Of course, you need to use a sieve with a hazard and purchase size approximately 80% of the ball size, because you need the balls staying on the sieve and the sample liquid dispersion going through. Now you can handshake or you can use a sieve shaker from Retsch. And there's a trick, just put a sheet of paper over here to this lid so that you do not have the cover of the sieve shaker here, this lid splat or made dirty by the sample. Yeah, just a piece of paper in between is very nice. And then you get it separated. The balls, of course, there's some liquid in, so you can flush it with more dispersant to get more sample or to recover more sample, and you have here this ground material separated. Then let's talk about the energy input. Yeah, we have talked about it a little bit, but here we can also compare the different systems, the G-forces, which can be achieved at maximum speed of the Emax, the mixer mills, and the PMs. And we see, of course, the Emax has the highest energy input, PM 100, and the PM 400 maybe the lowest. And the mixer mills, we are talking about control and nano, something in between, of course, the high energy input of the PM300. But what does it really mean? Is more energy input always better for the grinding results? Remember, I told you for dry grinding, this may also lead to caking effects. Maybe the moderate speed is better. What about the temperature? When you raise this energy input, also the temperature will raise. So the longer grinding breaks may be required. So do we have any active cooling options? What about the heat dissipation, which also depends on the mill geometry? So there are some ball mills on the market where this is not optimally solved because the heat from the jar cannot go anywhere because it's stuck in the system. So here an openly accessible jar with a lot of air around it is nice because the jars can be cooled just with an airstream. Or, of course, we can talk about active cooling. For example, with the MM500 control. Remember, -100 to +100 degree as the range. We can use, of course, the mixer mills and the Planetary ball mills. So we start at room temperature, but there's no active cooling for those machines over here. So after a while, you can really reach more than 150 degree in a jar, especially for wet grinding. You have the Emax here you can start with a 4-degree cold water, but after a while this also gets warm. Maybe not to the same extent, maybe it will stop over here with 70 degree, but yeah. And of course we have the fixed temperature of the cryomill with almost -200. And what does it really mean, and which system and which influences are we talking about? So we have to talk about the mill itself, of course. We have to talk about the sample, the fill-up quantity. Yeah, we have to talk about the grinding time. Do we use intervals or grinding breaks? Do we have active cooling? The jar material. We also have to talk about the grinding boards, the diameter, the material, and the number. And what has really a high impact on warming effects is that you get much more warming in larger jars when you use more or a larger number of balls. And of course, when you go into the machine with a high frequency or speed, you grind for a longer time, and maybe the intervals are not long enough. But also the filling level, again, keep this in mind, also influences the sample temperature. And when we are talking about cooling effects in PM, MM, 500 nano control, and the Emax, the same sample ground in the different system, no cooling breaks, just continuous grinding. You see that we reach more than 120 degree in a planetary ball mill at maximum speed quite easily. When we are thinking about the Emax, we end up at approximately 80 degree, only with the internal cooling. And the MM500 control, without any cooling added, it's more or less the same for the MM500 nano at higher speed. We ended up 60 degree. And now we can also go for the cooling options. We can set the second external cooling loop with a 4-degree cold water to the Emax, with a chiller. And then you see that we can drop the temperature from almost 80 degree to approximately 50 degree in the end. And when we use the MM500 control with 4-degree cold water from an external chiller, we end up at 30 degree, so more or less room temperature in hot summer. So there are drastic changes in the temperature development when we are using different systems, and also when we really cool actively. And what is also a nice point with the Emax and the MM500 control, we can start with a temperature of 4 degree when we let the temperature cool down prior to grinding. And then, of course, we can get lower temperatures in the end. So many options over here. And this has an influence really on the grinding result, because the temperature leads to agglomeration effects, to some different changes in the structures of the very tiny sample materials. And here's, for example, the task was to stay below 80 degree. And in the nano and 500 nano, there was not much heating, so we didn't require any breaks. And for the Emax, we had also the cooling available, so we didn't need any breaks because of the counter cooling options. And we compared it to a benchmark PM, which is available on the market, which has an energy or a speed of 1,100 RPM. And we saw that we needed 120 minutes net grinding time to come to the finest particles of 130 nanometer. But due to the warming here, inclusive of the breaks, the intermediate breaks, we required more than 600 minutes in total, so not very efficient. So really long process time to come to this 130 nanometers. With the MM500 nano, no breaks required, 120 minutes net grinding time required, was also the total process time of 120. Much finer particles because the warming was different, the agglomeration effects and the mixing effects were different, so we had better particle fineness in the end. And still the Emax here, the fastest, only 30 minutes have been required to come to the finest particles of 80 nanometer in this example, no breaks, so in just 30 minutes total process time, the sample was perfectly ground. So really the energy input, the geometry of the jar and the mills plays really a nice role on which fineness you can achieve in the end and how long does it take to come to this particle size. Then let's also see some application examples for the wet grinding. For example, here PM100 was used, 120 milliliter jar, 1 millimeter balls, some water in it, and you see the particle size distribution after 1 hour grinding with an intermediate value of the particle size, so D90 of 200 nanometer. And when we go for 3 extra hours of grinding, you see that it's shifted towards finer particles. And here you see that we reach a D50 of 100 nanometer after a while. When we use smaller balls, not the 1 millimeter balls, the total grinding time, but we change. Yeah, we start with the 1 millimeter and we change after 1 hour to the finest 0.1 millimeter balls. Same sample, same mill, same parameters. You see that we need 1 hour for the pre-grinding step, 2 hours for the fine grinding step, so 3 hours in total, not 4 hours in total. And we come to finer particles here, less than 100 nanometer compared to the upper example. So also the ball size has really crucial impact here on the grinding time and the fineness. And also here, just to show, this is a particle distribution before grinding of this barium titanate ground in PM200. And after 5 hours, it looks like that. So much narrower particle size distribution. And here the D90 is less than 100 nanometers. So 90% of the particles are smaller than that value. There are some other application examples for the Emacs. Here I will not show it that detailed, but I'd like to point out that the Emacs really gets its strength for the wet grinding because it has the cooling capacity, the best mixing options, crushing and impact and friction at the same time. So you can be sure that the Emacs is faster. We had it already shown in the previous example. Here another one, graphite ground in the PM. It took about 6 hours. Graphite is a lubricant and the sample smears somehow away from the ball. So grinding this material is really not easy, but the Emacs could do it in just 1 hour. So just in 1/6 of the time. Zeolite, our material. Here again, the Emacs was much faster, not 1 hour, but only 10 minutes. Barium titanate, 5 hours. The previously shown example was just done in 2 hours in the Emacs. So the Emacs is much faster, and additionally, it's usually up to 3 times finer than the PM. If you really need the fastest and the finest mill, then choose the Emacs. And some wet grinding example for the MM500 control. Again, very fine zirconium oxide balls, titanium dioxide was ground. You see over the time that we reach nice particles here. So already after, let's say, approximately 100 minutes, it's fully ground. Here is not much grinding appearing again. But the temperature development is very interesting. You stay below the 20 degree, so below room temperature when you countercool it. When you do not cool the same, then you reach more than 70 degree here. So the cooling capacity of the system is really, really nice for temperature sensitive materials. It's really cool. Yeah. So here you can really influence the temperature. Then let's switch to some specific applications, mechanical alloying and mechanosynthesis. I have mentioned this in the beginning already. What is it? This means that you have chemical reactions in a bore mill. You do not need liquid or the solvent. You maybe do not really need a Bunsen burner to heat it, as you know it from your school times, but something happens in the jar here. You see, we start with the white powdered material, and after a while it turns yellow, so something else has been produced. It's not the initial material anymore, but here a chemical reaction has occurred. And this can also be done for some metals, for example. Then we are talking about mechanical alloying. For mechanical alloying, you use the kinetic processes in a ball mill to fuse the components with the large balls together. So when the balls always hit the particles, they melt them together, fuse them together, and in the end, you will have a mixed particle with different sample properties in an initial one. So it's really an alloying process. And this is beneficial for small quantities when you have difficult ratios of the components, or when one of the initial materials is maybe cannot be fused by melting. So the traditional alloying process, for example, you need 150 degree, do not know, and it's already evaporating at this temperature when the other one only starts melting. So you cannot fuse them. But with this method, it's easy and it can be done. Requirements to the mill: long process times, many hours. So also the new MM400 with the long grinding time is really suitable now for this process, and high energy input. Now, of course, we are talking about Emax, the new PM300 here, but also, of course, the PM400 mechanical alloying system, and the 35 Hz system MM500 Nano and Vario. So the energy input is crucial. And also we need large balls for that, because we need the impact energy. Yeah, no friction, we need the impact. And the people doing this, I think you know that you maybe do not come to the 30% filling. You know that you have less material available, and this will lead to some more wear of the jar and the balls, but that's the way it is done. You need the energy input with the large balls and the free open space in the jars. And what are you doing when you're starting? You have no idea how to start. You can start with tungsten carbide or steel, the heavy materials, which bring in enough energy input to the system. And you can work with specific sample to ball ratios. And here commonly is used 1:10, but also you will find 1:5 and 1:15. What does it mean? If you have 15 gram of your total samples, this is 15 gram, this one and together, and you like to start with the most common ratio, 1:10, you have to add 150 gram of boards. When you have decided that you need tungsten carbide, and you have also seen that you maybe like to start with the 10 millimeter boards, you know the weight of one of these boards, and you can easily calculate how many balls you need to come to the 150 gram. So that's how it is done. And there are nice examples over here. The Emax really is a good system for that. For example, you can melt together germanium and silicium. Here before the grinding or the alloying process, two different reflexes for the different materials. And after a while, after 5 hours, the distinct reflexes of the initial samples is gone and something in the middle occurs. So new material has been produced. And here it could be seen that the Emax is really faster than the Planetary ball mill in the initial pre-grinding phase, and also in the mechanical alloying phase it was faster, and it was also cooler than the PM400. So I will not go in each detail here. It's part of the download package. You can, if you are interested in this, look this up, and also, of course, ask us, call us, write us an email, and so on. Then let's talk about really the chemical reactions. You mix some educts, and in the end you get some products. The usual way, maybe from school times, is that you have to overcome this activation energy. You remember maybe, and this is usually done by heating. The energy comes from the Bunsenbrenner, and you need some solution where you put the material in. So to get the different materials in close contact to each other, and this is done with a solvent. Can be water, can be really poisonous stuff, which is not really nice for the environment. And in classic chemistry, the solvents are required. There's a green alternative for the so-called green chemistry way, and this is mechanical alloying, where you use the ball mills. Again, you need the balls and the energy input by the balls and the mixing effects. And the activation energy now comes from the kinetic energy when the balls collide, and you have the mixing effects. So you do not need any solvents to bring the particles together and the materials, because the balls do the mixing. and you always have fresh surfaces because of the crushing effect. And the ball mills serve as a chemical reactor. This is a very interesting point, I think, because there are many advantages of mechanochemistry. You do not need the solvents, so it is eco-friendly, cost-efficient, safe handling, and faster. And there are different processes. So the reaction pathways are sometimes different than in the classic way. And this means maybe it can be faster. Maybe you can stabilize intermediate products, which is not possible with the classic chemical way. You can come to new products and you can get increased yields in the end. Just 2 examples for that. Cooling and MM500 control has, for example, an influence. So when you do not cool it, you will end up with a material which is called derivative 3 here in the synthesis of this zeolitic imidazolide framework, CIF8 product, which is a non-porous one, and you like to get highly porous material. So when you do it in a classic way or at room temperature in a ball mill, you end up with maybe something, yes, but there are not many pores in it. But you need the pores to capture carbon dioxide, for example. So you apply active cooling and you can stabilize it for a derivative 1, which is a highly porous, and you can now stabilize this material and use it further on. Second example, heating, again, MM500 control. So at the room temperature, you end up with, please do not ask me what it is, I'm not a chemical person, but you see it looks different than you when you do it at room temperature or when you use 80-degree warmed jars, which are just achieved with a thermal oil and a chiller. Yeah, something differently comes out in the end, and this is controlled again by the temperature. For the mechanical synthesis and alloying expert, we have special lids, so we can work at with the ration lids under inert atmosphere. So it's true for Planetary ball mills and Emacs and the MM500s. Here we can work with different inlays. So example here, the same lid with the valves can be used, and then you can put in a zirconium oxide inlet in, or you can put a steel inlay in, so you can use the same base with different inlays for different materials. Quite nice. And we have the grind control to monitor the temperature and the pressure, again for the Emacs, the MM500 Nano, and control and the Planetary ball mill systems. So that's what the software is looking like. So you get some nice curves for the pressure and the temperature development inside. And yeah, it's really nice way. And we also can here work with its inlays. So you can exchange, for example, like zirconium oxide inlay to steel inlay when you have different ways of working with steel or with zirconium oxide equipment. And yeah, it's quite nice. You can measure the temperature in range -25 to 90 degree, and for example, the temperature, the pressure up to 50 millibar. Yeah, so 5 bar in a resolution up to 50 millibar. Sorry. So again, all these details can be found on our webpage in the download package and so on. Just to close for the mechanochemistry, here the new MM400 is nice, and also the PM300 with the high energy input and the MM400 with the high grinding time. Yeah, so also the option to calibrate time and frequency is very nice because you exactly need to know what is in and what is going on. So for the mechanochemistry people, and the equipment I showed before is also very nice. Yeah, the Raman spectroscopy people maybe like to work with the transparent jars. If you need some samples at the same time, here this adapter for the 5 milliliter jars can be nice. For the MM500 Nano and control, we have this adapter available, which keeps plastic tubes, 2 milliliter plastic tubes, or the steel tubes. Yeah, here. And we have also multi-cavity jars for the Nano and the control, 4 times 10 milliliter cavities or 2 times 25 milliliter cavities for smaller sample volumes and more samples at the same time. Then, before I come to the end, I also like to give a short overview what is possible with biological samples. Here we are mostly usually working with disposable tubes, so Falcon tubes, wide mouth bottles, the single-use tubes, 2 milliliters, or Eppendorf tubes, you know them. And here we are talking about crushing more or less bacteria, algae, microalgae, yeast, so single cells. Yeah, here we are talking about cell disruption. We are also talking about sample tissues like tumor tissues, homogenization, also insects, so whatever, some plant materials. And yeah, as I said, single-use vials are required because it must be cheap and you have to throw them away after a while. Why are we doing this? We like to extract the RNA or DNA or the proteins, and also cooling here can be an issue, for example the proteins, because they denaturate at a certain degree of temperature, maybe 35-40 degree, depends on the protein. And here the procedure is also very nice. We have the cell disruption via bead beating. Yeah, it's for the yeast cells, bacteria, and algae. For example, this are the microalgae before this bead beating process starts. Then we use different adapters to put in the single-use vials. Single-use vials, 1.5 to 5 milliliter for the RNA and DNA extraction. Here we do not need much material. Or the Falcon tubes for protein extraction. We need a little bit more material over here. And we can do it with glass beads in different sizes. We use the smaller ones for microalgae, larger ones for yeast, and depends also on the growth phase of the cells, which ones are beneficial. Yes, the mills, MM4 most versatile because it keeps all the adapters, also the one for the proteins, the Falcon tube ones. The MM500 Vario can be used, and the MM500 Nano Control also can be used, and the control is also coolable, as I said before. The filling level for yeast and bacteria is that you fill in the, for Falcon tubes, for example, 50% with the beads and 60% of the nominal volume with the suspension. You think, okay, this ends up with 110%, but that's not true because the suspension goes between the beads, and then you end up with approximately completely filled tubes. For algae, we need more friction, so more filling level of the beads, 80% and 20% with suspension. And there must be a little bit free room and must not be too dry inside. Again, with this picture I showed you for the wet grinding, if it is too dry, it cannot move. So it must be really freely movable inside, and you have really to put in enough glass beads inside to have these friction points in between. Time, about 20 to 60 seconds for microalgae. For the other, it depends on the growth phase, and for the walls of the cells, yeast can be a little bit tricky, up to 7 minutes maybe is required. And about the cooling effect, you can start with an ice cold or ice water cold suspension. For example, then it has 8 degree, and you can then grind for several times. You can go back to the ice cold water and go back to the mill and so on. Do this in several steps. And for example, just to compare the MM400 over a vortex system, which is maybe also known to you, you see that you do or can stay below, let's say 13 degree with the suspension with the MM400, where the vortex is getting much warmer. And with the MM500 control, you see that we can even fix the temperature around 2 to 3 degree over here when we go with a 4 degree cold chiller, or even a little bit less. So here controlling the temperature is crucial, especially when you are working with proteins. And this is really nice that we have different options over here. And just to compare the bead beating process in an automatically system like a mill with a vortex, which is more manually and more individually, you see that we have much less variation in the protein concentration, for example, when we use a mill instead of a vortex system over here. The homogenization of tissue is also very nice. You can do it in the Eppendorf tubes or in the Falcon tubes. 30% of the tubes should be filled with tissue. Then you have to add some larger balls. 4 20mm balls or 3 10mm balls in the 5ml tubes. Why not only one? Because you need to decrease the impact effect a little bit, because you're talking about plastic tubes. And one single ball has too much room to move, and too much impact will result in breaking of the tubes. So several large balls, fill almost with buffer. Again, you will need to get away a little bit of the impact. And then it depends a little bit, up to 3 minutes, 4 or 5 maybe, and you can work with 25 or 30 hertz in the MM400. But you see that maybe there are some leftovers, like this tissue over here, and when you like to get rid of this, this is only possible in cryogenically grinding. Yeah, so you will have some leftovers with this procedure. It depends on you to decide, is it okay or not. And with the new tubes, the 2ml steel tubes, for example, this is very nice, because you can now really go for the cryogenic grinding also when you are applying for a lot of small sample volumes. And this can be used in the MM400, the Vario, and the MM500 hour control. Yeah, and you do not have the risk of breaking the 2ml plastic tubes anymore. Okay, before I really come to the end of this webinar, I have to announce something. We have a scientific challenge which starts right now. And when you scan this QR code, you come to a landing page where all the conditions are explained. So if you have any scientific idea, or you're working with the planetary ball mills, with the Emacs, or the MMs, the mixer mills already, just write us what you're doing, how you use the mills, and how you really impact for a better world in the future. So how your research really impacts more to a greener or more sustainable environment, or what else. So you will find everything on the page. Just screen and apply. And of course, there's something to win in the end. We will have on the PM 300 and MMs, which can be won. So please have a look at this. And if you have some questions about that, contact us, of course. Then I think it's just time to have some closing remarks. So you will receive an email with a download package. There are the presentation, application reports, videos, some specific documents, the Schiller specification for the MM500 control, and so on will be inside, and also the information about the scientific challenge. And yeah, please feel free to download it and to keep this information for your daily work and to improve it. Then we stay a little bit in the chat right now. So of course we appreciate your feedback, and I really looking forward if you like to email or ask us right now. So my colleague has been already very busy. I think it has been quite many questions coming in. Okay. So we cannot go through it, each question right now, but maybe I can have a closer look on what has been asked, which is more interest for everyone. Let's see. Okay, there was again the question with the filling of the Falcon tubes when we like to beat the bacteria, for example. So yes, you really have to assure that there are a lot of this tiny glass beads in, because you need the friction points to really disrupt the cells. When you only pour in 10 milliliter in a 50 milliliter Falcon tube, this is not enough. Yeah, in a 50 milliliter Falcon tube, at least 25 more 30 milliliter beads must be filled in. And then you can pour in, believe me, even if you pour in 30 milliliter beads, you can pour in 25 milliliter cell suspension, because the cell suspension goes between the beads as well. And then you can just close it. There's only a little bit room left, before the lid comes, and then everything is fine. You can shake it, and if you really are afraid that it's not tight enough, you can use parafilm and also to tighten it. Yeah, and then you get really perfectly cell disruption results, and you can use the proteins after a while. Okay. Then there is a question when tungsten carbide as a grinding material is required. Tungsten carbide, as I said before, has a very high density, and this means that it brings in a lot of energy input. And if you now have really very hard materials, let's say an ores can be very hard, or even teeth, human teeth can be very hard. Then maybe tungsten carbide is a good choice because you need this crushing efficiency of the 30 millimeter boards or 20 millimeter boards to crush the hard material. On the other hand, tungsten carbide tends to turn the sample a little bit grayish for the teeth. It will not be white anymore after the grinding. It will be a little bit grayish, but if you are looking for, do not know, some hazardous substances in the teeth, then tungsten carbide abrasion does not play any role. So it's just a color effect. Yeah. And on the other hand, if you have a sample material like bentonite, bentonite is cool. Bentonite seems to be hard and brittle, but if you put this in a ball mill and you put in too much energy in, or for example, you need tungsten carbide or even steel balls with a high speed of maybe 600 RPM, you will not get bentonite powder anymore. You will have just a layer of the material inside the jar wall, and also the balls will be covered with the material. So this is a very strong caking effect, and you will not be happy with this. So here, moderate or even low speed is much, much better to grind this. And maybe to work with agate, or maybe not in dense material, or not to work in a ball mill and go to a rotary mill instead. So yeah, really, it depends on your sample, your requirements, which speed, which mill, which type of accessories you're requiring. Okay, I think the other questions are maybe more or too specific. So at this moment, I'd like to close this webinar, and I hope you enjoyed. And please again contact us with every questions you might have. We are happy to answer it. So have a great day wherever you are, and bye.